Hello students, in this lecture we will continue our discussion on functional blocks. Specifically, we will study a special class of functional blocks that perform arithmetic operations or that serve as arithmetic functions. The outline of today's lecture is as follows. First, we will introduce the concept of iterative circuits made up of arrays of combinational cells. We will also describe them as blocks designed as iterative arrays for performing addition and also covering both addition and subtraction. Let us start describing the iterative combinational circuits. Note that the arithmetic functions or blocks are typically designed to operate on binary input vectors and produce binary output vectors, right? Also, the function implemented often requires that the same subfunction be applied to each bit position. Therefore, we can design a functional block for the subfunction and then use repetitively for each position of the overall arithmetic block being designed. The subfunction blocks are referred as cells, and the overall implementation is an array of cells. Okay, the cells in the array are often identical, but it's not always the case. So the cells, the subfunction block, are identical. Well, also due to the repetitive nature of the circuit and the association of the vector index with each of the circuit cells, the overall function block is referred to as an iterative array. Okay, so this is how we define iterative arrays. Well, in other words, the iterative arrays is a special case of hierarchical circuits, which are useful in, let's say, handling a vector of bits. Okay, for example, a circuit that adds two 30-bit binary integers. We will see the examples of such iterative combinational circuits. Here we have an example of a block diagram for an iterative circuit. This is a 1D iterative array that operates on n inputs and input vectors and then produce n output vector, right? In this case, we can see that there are two lateral connections between each pair of cells in the array. These are the cells, right? One from this Y, from left to the right, and then the other is running from right to the left. Those are lateral connections. Also, we can see that this one, right? These optional, let's say, connections indicated by dashed lines. Probably you cannot see in detail, but these are the dashed lines. These are the at the right and then left end of the array. Look, an arbitrary array can use as many lateral connections as needed, depending on a particular design, right? And the definition of these functions, which is associated with such connections, is very important in the design of the array and its cell. In particular, the number of connections used and their functions, which both can affect the cost, right, of the iterative circuit and as well as its speed. These kind of iterative arrays can be considered as a special case of hierarchical circuit, useful in handling vectors of n bits. One of the common operation is addition, right? A circuit that adds, for instance, two 32-bit binary integers. If you want to build a combinational circuit to perform, let's assume 32-bit integers, right, n is equal to 32, then the total number of inputs to the combinational logic circuit equal to 66, right, 66, including the carry-ins from the addition. And also the truth table will have 2 to the 66 number of rows, which is going to be a very huge, very tall truth table, right? And then the equations can go up to, with the 66 input variables, right, which will lead to the equations with huge number of terms. That is not practical for circuit implementation. So in such situations, one may use the advantage of regularity to make the design feasible using such iterative arrays. We said that one can design a function block and use it repetitively for each bit position of the overall arithmetic block, okay, that's being designed. For instance, an addition operation. We will see different examples of functional blocks in the next slides. In particular, we will see the examples of half adder as a functional block for performing 2-bit to input bitwise addition. We will also see full adders for 3-input bitwise addition, and other examples of addition blocks such as a ripple carry adder and then carry look ahead adders. Again, due to the repetitive nature of the circuit and the association of a vector index with each of the circuit cells, the overall functional block is called as iterative array. So first example of this functional block is called a half adder. Well, combinational circuit that performs the addition of 2 bits is called as a half adder. It's a combinational circuit, right? This half adder is actually an arithmetic circuit that generates the sum of 2 binary digits. Okay, so the half adder circuit has 2 inputs and 2 outputs. The input variables that needs to be added, and then the output variables produce the sum, denoted by S, and then carry, right, denoted by C. And actually we assign these symbols X and then Y to the 2 inputs, S for the sum, C for the carry for 2 outputs. We can build a truth table for this half adder. We can just visualize it. We can list the truth table for easy interpretation of the addition. For example, as listed here, this is the truth table. We have C output, right, and then sum bit, carry bit, and then 2 inputs, X and Y, 0, 0, 0, 1, 1, 0, 1, 1. Note that the output C is only 1 when both X and Y is 1, right? While the S, the sum bit, S output here, represents, let's say, the least significant bit of the sum. We can see that S is high when the input are different. 0, 1, it's 1. 1, 0, it's 1. So 0, 0, 0, 0, 1, 1, 0. This reminds us one of the operations that we have reviewed, right? In other words, the exclusive OR operation. So again, given 2 input, 1 bit with binary adder, okay, the half adder performs the following operations, right? The following additions. Well, we have learned about binary addition in the earlier lectures. So we know that 1 plus 1 is 1, 0, right? The sum is 0, we have carry equal to 1. 1 plus 0 is 1, and then 0 carry. 0 plus 1 is 1, and we have, this is S, right? This is sum output, this is the carry. 0 plus 0, 0, and then we have the carry. So it's a good time to review all those binary arithmetic. Now the question is, how can we express a half adder using Boolean functions, right? So first, a straightforward method is to form the K-map for S, sum, and then for the carry. For two variable K-map, right? This is S and then carry, based on the min-term locations. right? And then we can see that the sum, okay, we can see that the sum is equal to the following. So x, okay, and y complement, okay, we'll circle this one. And then x complement, and then y, another one. So this definitely is the exclusive OR operation. We remember that. And this also has another form, right? POS, product of sums form, the representation for the exclusive OR operation, as shown here. This is sum of products. For the C, for the carry, we can get, okay, x and y. This is the AND operator. So the carry is an AND operator. Right? So based on these equations, we will see several other extensions or implementations. So it's easy to show that based on these exclusive or these AND operations, we can derive the following set of equations for the half adder. They are quite equivalent, either using Boolean algebra techniques, right, such as function complements or De Morgan's law. We can verify easily that all of them are quite equivalent. For instance, here A, B, and then E are the sum of products and the products of sum, and then exclusive OR implementation specifically for S, for the sum. Well, in C, in this case, the C function is used as a term in the AND NOR. Look here, this is AND, and then NOR, implementation of the S or sum. And in D, we see that the function complement, the carry complement, is used as in this POS term, product of sum term, right? Also, when it comes to the implementation, the half adder can be implemented with one exclusive OR gate, as shown here, and then one AND gate, right? So sum, okay, here x and then y inputs, each is 1 bit, right, length input, and then this is an exclusive OR operator. We have S, and then the carry will be defined through the AND function, right? We can verify this is by simply looking at the truth table. Well, we can also use a NAND gates, right? NAND only implementation by using the following, representation, Boolean representation of our sum and carry for half adder. So we'll use 4 NAND gates and then 1 inverter, right, to implement the equivalent NAND only implementation of the half adder. We said that NAND is a universal gate, right? Let's try to break down and then prove that this NAND only implementation is equivalent to this Boolean representation, right? So it's easily to check. So NAND, at this output we'll have x, y, and then which will be complemented, right? X and y, right? And then another output is, so x and y. This is x and y. Well, x and y goes to this second NAND gate. Let me just write down first, second, third, and fourth NAND gate. So the second NAND gate will have this x and y complement as input, and we have x here as input to this one. So the output of this second NAND gate will be x, okay, and we have x and y complemented, and NAND, right? So we will have another complement here, right? And then the output of the third NAND gate here, okay, input, one of the input is y, and the other input is x and y complement. The output of this will be equal to y, and we have x and y, right, complement, and another complement, right? This is the output of NAND because of this bubble, right? And now what we have here at the output of the, so these two will go to the fourth NAND gate as input, and then the output of this, let me just quickly erase this. The output of this S should be equal to x, okay, and y, x exclusive for and y. So now what we have to do is just to simplify these two, we can apply the De Morgan's law, right? Let me write it down here. X naught, this is, okay, and then we have another complement. So if you apply De Morgan's here, so x complement, right, the sign changes to or, and then we have x and y double complement, then we will have just x and y, right? So after applying De Morgan's. Well, also similarly here, if you apply De Morgan's, we will have y complement or x and y, right? So these two will go as input to the force NAND gate, right? So if you write down these, and we have NOR, right? This will be the output. You just need to verify now if this expression is equivalent to the exclusive for. Yes, so if you apply the distributive law, we can check the equivalence. Because here we have x and y, right? Two same term. Yeah, that is a pairing in the product of sums, right? So this will simplify to, if we apply distributive law, x, y complement or x, sorry, this is x, y, and then we have another complement.
Fine.
So this is an XNOR operation, which is equal to x exclusive for operation, right? And now we are left with a C. So C, okay, the output of this first NAND gate goes to the output carry, right? So if we invert x and y invert, by invert then we get x and y. So here we have another functional block example. We call it as a full adder. Full adder is also a combinational circuit that forms the arithmetic sum of 3 input bits. Here we have 3 inputs. And besides the 3 inputs, the full adder will have 2 outputs. Okay, 3 inputs are denoted here by x, y, and then z. And then 2 of the input variables, as we denote here x and y, represent the 2 significant bits that needs to be added. The third input, which we denote here as z, represents the carry from the previous lower significant position. So it's a carry in. The 2 outputs, we need these 2 outputs also because the arithmetic sum of these 3 bits, okay, that range in the values between 0 to 3, and then the binary 2 and 3 need 2 digits for representation. So for C, that's why we need 2 outputs, CS. Again, the 2 outputs are designed, designated, or denoted, let's say, by the symbol S for sum, carry for C, as we have introduced in the half adder example. Okay, the binary variable C here, S, gives the value of the bit of the sum, and then the C binary variable gives the output carry. Output carry, this is input carry, right? Carry in. So we have the S, right, as a result of summation. Okay, 0 plus 1 is 1, 0, right? And then 0 plus, okay, 1 plus 0 is 1. Also 0, 0, 1, 1, 0, 0, 0, 0. So carry out C only happens when you have either this case or the following. So we have two different possibilities for the z, as shown here in this example, right? When z, okay, all of them are 0, we don't have a carry in z, then it is equivalent to half adder. However, when we have a carry in z of 1s, then this will represent the full adder, let's say, of block, functional block, full adder circuit. Here we have the truth table of the full adder in this table, right? The values for the outputs S, right, and then C are defined or determined from the arithmetic sum of 3 input bits. This is the difference as compared to the half adder, right? In half adder we had only x, y, but in full adder we have another variable called z. We said carry in from the previous addition. Look, when all inputs are 0, right, the outputs are 0, S and then C. So S is 1 equal to 1 when only, as you can see, one input is equal to 1, one of the input, or when all 3 inputs are equal to 1. Okay, if one of these, or all 3. The C, the carry out, the C output, okay, is a carry of 1 if, as you can see, 2 or 3 inputs are equal to 1. 2 or 3 inputs are equal to 1. Right? We can form the map, the K map, okay, for 2 outputs to represent the full adder in terms of the optimized Boolean expression, right? So this will be the example of the K map for 3 variable K map, where we put the midterm locations, right, in the K map and then form the grouping. Now we can form the grouping of the minterms. Let's start with the S, right, sum, and then here we have the grouping of the carry. So if you remember, in one of the classes I told you that the odd functions usually will have a checkerboard pattern on their K map, right? This is an example of the odd function. So now let's try to get the Boolean expression for this, right? So S will be, let me write it down here, S, okay, S is equal to, all right, so first one, let's start with this one, right? X naught, Y naught, and then Z, or, okay, second one. So here what changes? So X naught, okay, Y, and then Z naught, right? And then let's take a look at this one. X, right, Y naught, and then Z naught. And we have the last one, which will be equal to X, Y, Z, right? This is the Boolean expression for the full adder, and we can see that this is a 3-bit exclusive OR function, right, which can be simply or written in compact as X exclusive OR operator, Y, and then exclusive OR operator, and then we have Z. Okay, and then for the carry, with this C, we will have 3 terms, right? C will be equal to XY, XZ, and then YZ, right? Can you check? Look, from the truth table, we see that the carry bit C is equal to 1. Okay, let's start from this. 1 if x and then y is both are 1. That's first case, right? The sum is 2. Or if the sum is 1 plus we have the carry in. Okay? So sum between x and y is 1 plus carry in, or we have x and y 1. So in that case, we have the c equal to 1, right? So this observation allows us to write down the c differently. So first we set x and y if it is 1, right? Then c is 1, right? So let us write this. C is equal to x and y, right? If these two are 1, then it is 1. Or we have another condition, so related to z. Okay, so we can write it down, x exclusive or y, right? And then z. Okay, so we know that the exclusive or true is stable, right? If x and y is different, right, then we have output 1. And if this is different and then we have z is 1, then c will be 1. I mean, c will be high. Otherwise, okay, so we're trying to put this table into this mathematical form. Well, why do we care about putting in this form? So having this c in this form allows us to interpret like x and y as carry generate, and then this term as carry propagate. So carry generate, carry propagate, right, for the next addition. So from the K-map, we obtained the following representation, S for the carry, for the sum, and this is the exclusive OR for 3 variables, and this one is the carry, right, as we said. And then by rewriting the C in this form allows us to interpret this as the first term as a carry generate, and then second term as the carry propagate. Here we can see the implementation of full adder schematic as shown here. So we can implement the full adder using 2 exclusive OR gates, 2 AND gates, and then 1 OR gate. This is the full schematic, full adder schematic, right? In the previous slides, we defined the inputs as x, y, and then z, right? Z is a carry from the previous addition, and then c, carry out. But here we denote them as x. Instead of x, we have a. Instead of y, we have b here, and then z, we have ci, right, index. And then we also have the c. In addition, right, we said that the g, okay, the carry can be represented by 2 terms, right? Let me write it down here. So here, from the previous slide, what we have done is c, let me write it down here, is equal to x, y, right? This is the first component, first term of the carry. And then we have x, exclusive OR, right, y, and then z. Well, we said that the first term here represents the carry generate. Carry generate. Well, second, carry propagate. We can, interpret as carry propagate. All right. So now, if we take a look at this schematic here, we have the G denoting the carry generate, and then P denoting the carry propagate. What are they? Well, the first term, also carry generate, is a function actually, which specifies the condition when the full adder, okay, can generate a carry, or will generate a carry corresponding to its carry input. So it will generate a carry, right, correspond to its input. So here we have OR, and this is carry in. We have and we also have propagate. So it will generate a carry. So what about the carry propagate, the P? The carry propagate is also a function that specifies the condition when a carry input can propagate to the carry output, right, in a full adder stage. So carry input propagate to carry output, right? If P is 0, then this is AND gate, then the carry will not be propagating, right? So here we have the situation where we can see the full adder generating the carry to the next, right, calculation. So also we can see here, right? So carry output is equal to carry generate, right? Generate or gate, and then this is carry input propagate AND gate, right? Propagate and carry in. Well, in this case, x is equal to a, right? I should have written that way. B is equal to y, and a exclusive for b and then c. Okay, a and b, or a exclusive for b and c. That would be the correct way with a new notation. Now we have seen the examples of adders, right? Half adder and then full adder, and then also their mathematical Boolean representation, and also schematic implementation examples. Now let's take a look at the binary adders. So what are binary adders? Binary adders are, again, arithmetic circuits that usually comes in the form of half adders, full adders, and they are used to add together two binary digits, right? So to add multiple operands, for example, we bundle logical signals. Signals is bits, right, inputs, together into vectors, and then use functional blocks. So adders that operate on vectors. Here we have example 4-bit ripple carry adder example, right? So 4-bit ripple carry example consists of the 4-bit, let's say this is the carry in, this is augent, right? And then this is addend. So A, B, we want to add 4-bit A to the B, and also we want to consider the C, I as a carry in, right? And then we have sum and carry out, right? Sum and then carry out. In this case, input is represented as a vector. Well, schematically, we can construct binary adders using a cascade of, for instance, full adders that we will see shortly for performing this kind of multiple bit addition operation, for instance. Here, this figure, this graph shows the interconnection of 4 full adder blocks, right, to form a 4-bit ripple carry adder, binary adder. We can see that the augment bits of A and then the addend, right, bits of B are designated by subscripts in increasing order from right to left, with the subscript 0 denoting the least significant bit, and in this case subscript 3 denoting the most significant bit, right? We also know that the carries are connected in a chain through the full adders C0, C1, C2, C3, and then C4, right? So in other words, the input carry to the parallel adder is C0, and then output carry would be C4 final, right? So here, as we can see, that this is an example of a parallel binary adder that produces the arithmetic sum of two binary numbers, okay, using the combinational logic in each full adder inside, right? In other words, the parallel adders in this specific case uses, right, 4 full adders in parallel with all input bits applied simultaneously, okay? So all of these input bits are applied simultaneously to produce the sum. This is output, right? And then also we know that the full adders are connected in a cascaded form, in a cascade. Also, yeah, so here the carry output propagates from one full adder to another full adder until the we get the output carry. Well, why do you think that we call, this parallel adder is called as ripple carry binary adder or parallel adder, right? It's all about the carry in, right? So C0 in this case may appear to be 1, okay? And then if we have carry input, that will propagate through many full adders to the most significant bit. And these kind of parallel adders is or referred to as a ripple carry adder. Why ripple? Just imagine of throwing or dropping a small stone in a pond, in water, and then you can see the ripple effect, right? That's why it's all about the carry is rippling. If there is a carry, input carry, it will ripple until the last one. Propagate, in other words. That's why it's called as, most of the time, ripple carry adder. Ripple carry 4-bit, n-bit, ripple carry adder. Now let's consider the subtraction of unsigned binary number. Subtraction, right? So we have minuend and then subtrahend, right? We can have two different cases. So let's briefly summarize this in algorithm. So first, subtract the subtrahend n from minuend. Well, in the first case, we don't borrow if the minuend is greater than or equal to n subtrahend, right? And the result would be a non-negative number, and then we can obtain the correct subtraction. So in another case, so if we have the following case where we need to borrow, the case where our subtrahend n is greater than minuend. Well, in this case, the difference would be m minus n plus 2n is subtracted from 2n. And then the minus sign is appended to the result. So here, when we perform unsigned subtraction, okay, we have the case 1 when minuend is greater or equal to subtrahend, and then case 2 when the subtrahend is greater than minuend. Then we will have to do one more step to obtain the correct answer. In other words, m minus n plus 2n is subtracted from 2n. 2n here represents the value of the borrow, okay, in to the most significant position. So let's take a look at the following example. So in the first case, what we have our minuend greater than n, right? N is our subtrahend, right? We can quickly check this. And then in this case, we have to make the borrow, right? So we will borrow. Let me zoom. Okay. So we will borrow into this. So we have 1, 1. And then we do borrow into this. 1 and then 1. So this will be 0 and then this will be 0, right? So 1, 1 minus 1 is 1, right? 1. And then here 1 minus 1 will be 0. And here we have 0, 0, 0. Here, this is the case where the subtraction is correct because, right, we have the first case. The minuend is greater than subtrahend. Well, what about the second case? Right, in the second case, so minuend is, this is our n, this is our m. So n is greater than m. So we will get negative, we should get negative output. Let's say output. So in this case, what can we do is we have to borrow. We did this kind of subtraction in a lot of these subtraction examples or exercises in the previous class, right, in the previous lecture. So let me go through it quickly again as a reminder, as a recap. In the first case, right, this one, we need to borrow. The most significant bit is 0. Introduce, okay, some borrow 1. Okay, so we will borrow. This will be 1, 1, right? Okay, and then we borrow from this 1, 1, and then one of them will be, okay, gone, right? And then we need to borrow to another one. 1, 1, okay, and then this will be 1, and further we borrow here, right? 1, 1, and then this will be gone, one of them, right? So look, 1 minus 1 will be 1, right? And then 1, we are left, minus 1 is 0, right? And then 1, okay, this is 2, 1 minus 1 is 1, right? And then here we have 1 minus 0 is 1. However, this result is not correct, right? This result is not correct. Well, we can check in decimal numbers why this is not correct. In base 10, this will be equal to, to the subtraction of 4, this is 4, minus 7, then we should get minus 3, right? But this is not a minus 3. This is a 4, right? If you convert to a decimal from binary. In order to correct this problem, we need to perform like 2 to the n. Well, 2 to the n, right? Correctly. So this 2 to the n represents the value of the borrow into the most significant bit position. So this is our borrow, and here is our borrow. So if you subtract now 2 to the n minus the output, right, then we will have correct result of subtraction. This is equivalent to 3, right, in decimal, if you convert. And we just append the minus. So let's take a look at further examples of how we can implement this unsigned subtraction. Now let me summarize the subtraction of two n-digit number. In base 2, we consider m minus n, right, in base 2. So we can have two different conditions. So okay, first is subtract. Okay, we have n is subtrahend, right? N from minuend m. So let me t. Okay, general, this is what we want, right? We want to subtract. So first situation, okay, is when m is greater or equal to the n. In this case, no end borrow occurs. We don't borrow from the n. And the result is non-negative. Okay, non-negative. Second case, that's what we also discussed, right? When n, right, the subtrahend is greater than m. Well, in this case, what we did is we took the difference, right, in the previous example of, let me write it down this way, m minus n plus 2 to the n. Okay, so the output of this is subtracted from 2 to the n. And then we assign, or we append a minus sign to the result. So basically 2n minus m, right, minus n plus 2 to the n in the second case. And then we append minus, right, minus sign. So subtraction of a binary number like this, from the 2 to the n, and to obtain the n-digit result is called as a 2's complement of the number. Okay, let's resume, and then we will see other examples. I mean, we will study what is 2's complement or first complement. The subtraction of 2 to the n minus n is equivalent to taking the 2's complement of n. Look, if you want to implement this adder subtractor in a circuit, For example, if we wanted to both unsigned addition and then subtraction, then we may require to build a sophisticated or complex circuit. The circuit that has separate adder and subtractor, and also the circuit that performs 2's complement. Okay? And also it may involve a multiplexer or combinational logic circuit. So this is complex, relatively complex circuit. Now the question is, can we simplify? Can we simplify this adder subtractor circuit for performing both addition and subtraction, right? And our next goal becomes to build a shared simpler logic for both addition and subtraction. Simplification of this approach can be done through so-called complementing approach.